Okay, so we talked about martensite in theory from a crystallographic point of view. I want to just look a little bit at carbon steel in specific, right, and why, right, just sort of experimental things about why, when we say about Kurgamov-Sachs and Nishiama-Wasserman, why it's so hard to decide. So here's just the pull figures for potential austenite or potential martensite variants for both the Kurgamov-Sachs and the Nishiama-Wasserman orientation relationship. And so this is a grain, this is from a austenite grain that's perfectly aligned, right? So the C axis of the crystal, right, it would be 1, 2, 3 dots on this pull figure, the 001, 100, and 010, perfectly aligned. And then after the transformation, we get all of these different orientations. So for Kurgamov, if it obeys Kurgamov-Sachs, we get 24 variants. The Nishiama-Wasserman orientation relationship, these 2 points actually move together. So these 2 variants, these pairs of variants actually come together. And there's only 12 distinguishable variants if it were exactly Nishiama-Wasserman. Except, of course, like everything in steels, it's never these 2 ideals. In reality, it's somewhere in between, and it's irrational. And so this is a measured pull figure of a single crystal austenite grain that transformed to martensite. Did you have a question, Tyson?
No, this slide is not including
the Is including what?
It's not including
It's not? No. Oh. Okay, I stuck an earlier draft up. I'm sorry. So I will update Carmen with the new one. Thank you for letting me know. So what we see here, this is actually an experimentally measured pull figure, right? And we see these cloud of points, right? They're not nice, clean clouds. And the question that comes up is this actually a variation in the orientation relationship? Is this due to previously existing orientation gradients in the austenite grain, right? Was there already lattice curvature there? Is this a result of the plasticity, right? Is this a result of local fluctuations in carbon concentration, right? From a mechanistic point of view, we can think of many reasons why we would get this, right? So I just want to sort of point out the scale of this. So if we go back to our phenomenological theory, we can describe the deviation from the ideal Bain orientation relationship to what we actually measure by a set of 3 angles, right? These are 3 Euler angles. They describe the rotation between the Bain lattice and the actual measured lattice. And if looking experimentally, we see that there's a fairly large deviation. On each one of these angles, we have a half width, full width, half maximum of about 6 degrees, right? So that's sort of the plus or minus 3 degrees for each around the rotation. So that means within a given sample, we have martensite variants that appear to cover the whole spread of possible orientations, all the way from Kurgamov-Sachs to Nishiama-Wasserman. So that means those clouds of those habit planes that we saw, right? They're experimentally, right? This is sort of what we see, but it's not just the habit plane, right? That habit plane could also be rotated. Right? You've got so this is just sort of an indication of the degree of spread. So remember, in low carbon steels, right, where you have a habit plane that's close to 111, and we have a Kurdyumov-Sachs-like orientation relationship, right? And we have at low volume fractions we have twins, and if we look at the evolution of the martensite with respect to the carbon concentration, we see a general decrease in the martensite start temperature, right? So carbon stabilizes the austenite phase, right? And if we look at the decrease in martensite concentration and the increase in retained austenite, right? So this laugh martensite, this you can think of this as slipped martensite, right? So at low carbon, we have 100% slipped. Once we get up to about 1% carbon, we're at 100% twin martensite, right? And we also have an increasing amount of retained alpha. As we move into the medium carbon, right, our habit plane changes. Now we're close to 115, so now we're in this regime here, right? I mean, close to 225 of the habit plane. We still have a carbon Kurdyumov-Sachs-like orientation relationship. We also can get some acicular those lenticular plates. Once we go to higher carbon, our orientation relationship shifts to close to the Nietzsche on the Wassermann, and our habit plane moves to the 259, right? And now we're completely twin martensite, right? And we get these big lenticular plates. Okay. And so most alloying elements are going to tend to reduce the martensite start temperature, right? And carbon is the most effective at doing this. Cobalt and aluminum are fairly neutral with respect to the martensite start temperature. Right, and here we see basically this is the hardness and the carbon, basically just the hardening curves, the the strength of the martensite is with respect to the austenite phase. Right, so here's our strength of our austenite. Here's our strength of our martensite. Right, and carbon is by far in plain steels is the most significant role in strengthening. Right, and we also get a modest boost in strength from aging. Right, we slightly age harden, right, at room temperature or below. And we'll talk more about this as we go into the heat treatment. Right, and this basically gives us just showing the effective yield strength versus the carbon content. Right here we have our slipped or laugh martensite. Here's our twin martensite, and they behave pretty much the same, but we get again, this just shows the significance of strengthening that we get with the addition of carbon, and we get these Hall-Petch-like relationships, right? And right, so we can still relate things back to free slip lengths, but we've got to. It's not as straightforward as a simple grain structure, right? Because we've got lath thickness, right, and the subgrain structure. So we got packet and block grain boundary sizes. So there's a lot more going on here, but we do see a Hall-Petch-like relationship with the size of the martensite lattice. Okay, so that sort of wraps that up. There is a fantastic course available, full semester course on the heat treatment of steel, so just on this lecture part. At a lot of universities, most places in the U.S. don't actually teach like whole steel processing courses anymore, but a lot of places where structural steel is still made in great quantities, like China and India, there is a real need, and so this is a set of course notes, and I've extracted some slides from there. The whole set of courses, the whole thing is actually like 800 slides just on the heat treatment of steel. So this is less than 10% of the material that's presented in there. And if you want to know the theory of the effective rate of heat transfer based on the viscosity and salt content of a quench and the relation of that to the degree of martensite formation, and need to be able to calculate that from fairly basic principles, this is your source, and Professor Kumar is your guy, right? Okay, so just a reminder, we talked about this at the beginning of the steels, but if we look at, we can basically classify them into low alloy steels and high alloy steels, right? The low alloy we can break down into low carbon, medium carbon, and high carbon. The plain steels basically just being iron carbon. High strength low alloy steels typically have chromium, vanadium, niobium, and molybdenum. Heat treatable has the same sorts. Remember, there's typically manganese in all of these, right? And then the high carbon steels, again, two big categories of high and tool steels, right? With the tool steels being very high strength, very high work hardening rates, but limited in ductility, and then stainless steels, or austenitic stainless steel. So basically, as we go from left to right on this, we have low cost, low strength, high ductility to high cost, high strength, low ductility, right, as we move across the chart. And so here's a chart with the phase diagram, but we've labeled all of the critical temperatures and points on here, right, and denoting them AC, right, for heating, right. The ones that are going to be really important that we're interested in is the A3, right, which is right here, the austenite, and A4, right? And so these are the two that are important for describing this shape of the austenite phase region. So if go back to our sort of equilibrium phase diagram, we can break down all of our alloying elements based on whether they're austenite stabilizers or ferrite stabilizers, right? Austenite stabilizers, right, tend to be FCC, right, well, with the exception of zinc, right, they're more soluble. Carbon is more soluble in them than ferrite. I mean, than in the ferrite. These tend to segment into the austenite, right? And then we also mentioned that elements carbon and nitrogen are interstitials, are also very strong austenite stabilizers. But these are all in the solid solution rather than in interstitial. The ferrite stabilizers tend to be the BCC elements, right? And we can say titanium and zirconium in there because they actually exhibit BCC phases, even though they're HCP at standard temperatures and pressures, right? And chromium is a bit of a special case, right? It sort of does some things that are a little different than depending on the concentration, right? But all of these tend to decrease the amount of carbon that can be dissolved in the austenite, right? If we decrease the amount of carbon that can be dissolved, it means that we have more carbides, right? We have more free carbides for a given carbon content. Chromium initially lowers the A3 temperature, raises A4, so expands the austenite phase field. Then as you keep going, it starts to do the opposite, right? And then close the size of that austenite field again. So we can sort of break these down into 4 classes of behavior with respect to the austenite phase field, right? So the first is this open field, right? So basically, our austenite region extends all the way down to room temperature, and so steels with large amounts of these alloying elements, nickel, large amounts of manganese, you can have significant amounts of retained austenite, so these are good for developing austenitic steels, right? And those are the primary. But notice these elements, right? Palladium, platinum, iridium, osmium, rhenium, right? You start messing with those, you get real expensive real fast. Right? So class 2, right, is an expanded field, right? But it's not open all the way down to room temperature, right? And your interstitials tend to do that, right? Carbon and nitrogen are the primaries, but also copper, zinc. I'm not sure how practical gold is, but it has that effect. So adding FCC elements will tend to expand the gamma field, right? If we close the gamma field, meaning that, right? So now here's our A3 and our A4 points, right? So this is our austenite field here, right? Right, there's a whole lot of elements that tend to do this. Basically, strong carbide formers, right, will tend to do this, and the delta phase, remember the high temperature ferrite and the low temperature ferrite become a continuous field, so we lose the peritectic reaction on the phase diagram, right? And so steels that are being developed for magnetic properties, such as transformer steels with fairly large percent of silicon, we can avoid the gamma, we can avoid austenite completely. We can heat to very high temperatures in the ferrite field to grow large ferrite grains. Right. And the last case is where we shrink the gamma field, right? Boron is the primary element to do that, and the more carbide formers that we can put in, right? The issue with this is we have a lot of intermetallics and other compounds that can begin to form, right? Okay. So basically, no matter what we put in there, we're going to lower the eutectoid carbon content, right? Titanium and molybdenum are very effective at doing so, right? So the example, if we have 5% chromium, our eutectoid is 0.5% carbon. If we don't have the chromium in there, we can get 0.8% carbon in. High-speed tool steels, right? Because of the alloying, we have eutectoid point at 0.25% carbon, right? High-speed steel is basically what we make what all machining tools used to be made out of before carbides, because they had very high manganese content and other alloying, so they get exceptional work hardening rates. Right? Basically, you can think if your workpiece that you're machining hardens faster than the tool you're cutting it with, right? Eventually, you reach a point where you go the other way, right? And now your workpiece is machining your tool rather than your tool machining your workpiece, right? Elements, so the eutectoid temperature, right, can be austenite stabilizers, right, will lower the eutectoid temperature, right, meaning we're retaining austenite to lower temperatures, right? Ferrite stabilizers raise the eutectoid temperature, right? And this just shows the effect of the different alloying elements to do so, right? And you can see how effective titanium is at raising the eutectoid temperature, right? And the effect of the amount of carbon that can be, this is the eutectoid carbon, this is the percent of the alloying element, right? And again, you can see adding small amounts of titanium drastically reduces the amount of carbon you can put dissolve in your austenite. Right? So we can rank these, right? This is the relative strength of the different alloying elements as either ferrite formers or austenite formers. Right? So again, you can see zirconium, titanium, tin, very good at stabilizing ferrite. Carbon and nitrogen are interstitials, and our manganese are our most effective austenite formers. Right. Yeah.
The big effects from zirconium titanium, that things to do with the HCP structure.
Yeah, the HCP is, well, so titanium at elevated temperatures and zirconium both will adopt BCC structure, right? They both go to cubic, right? So they're much similar to the BCC ferrite than they are to the FCC austenite, right? Even at, you can stabilize titanium and zirconium in their cubic phase pretty easily at room temperature, right? So it's not so much the HCP, it's the BCC. The BCC-like nature of those elements as well.
So what does it do with the more effective stabilizer than other elements?
That's a first principles type calculation, right? There's why specifically an atom. I mean, I can answer it. You can answer it for austenite, right? Because the interstitial this is these are going interstitial, right? So that is going to stabilize the austenite because there's a lot more room in the austenite for the interstitial phases than in the BCC. Specifically asking why the group 4 and tin are such effective, so effective at stabilizing the ferrite. I don't have a simple answer, right? It has to do with the electronic structure, the energetics of the solid solution, the potential, the bonding potentials between the different elements, right? There's no simple answer, right? Sometimes we don't necessarily know why. It's just we notice group 4 elements are pretty good, right? I don't know of any commercial steel that uses hafnium, but my guess is that would be an even more potent stabilizer than titanium or zirconium, right? Because it's the same family, but it's a larger radius, and the cubic hafnium phase is more stable than either in titanium or zirconium, right? So I could guess as to what would happen, but I may be wrong there. So I don't really have an exact why. So if you look in handbooks, you see diagrams that look like this, right, which basically sketches out the shape of the austenite phase field with the varying alloying elements. So we can see here chromium is a ferrite stabilizer. So as we add chrome, our austenite phase field shrinks, right? So what this diagram is I take the phase diagram and I delete all the other lines except the outline of the austenite phase boundary, the austenite phase field. And then I plot that for different alloying compositions, right? And on the other hand, manganese is an austenite stabilizer, right? So we can look at others, right? And so we see the effect here of the austenite field with additions of titanium, right? So this is less than 1%. 1% titanium is this little circle up there, right? On the other hand, we need to add 15% chrome or 20% chrome to get the same reduction of the phase field, right? Okay. Okay. So then, remember the austenite stabilizers and the ferrite stabilizers want to partition, right? As the different phases grow, right? They don't necessarily want to stay. They're not going to stay uniform, right? So as we grow ferrite, we're partitioning, and that partitioning rate is going to be governed by diffusion, right? And so the growth rate is going to be affected by the rate of the slowest diffusing species, right? And again, with our FCC gamma phase stabilizers are going to partition into the austenite phase, right? So nickel, manganese, platinum. Right? Ferrite, on the other hand, we're going to partition these. All right, these tend not to partition, right? Because we're at that. Remember, we talked about how carbon diffuses fast, quickly, right? And other solid solution elements go slowly, right? And so these go too slow to effectively partition when we're cooling down, right? When we're heating up, we have more energy, right? Partition more readily, right? So we're not at, when we're cooling down and we're growing ferrite, we're not at a true equilibrium. But the diffusion of the interstitial species is so fast, right, that it takes over, right? And this basically shows the reaction time. So we see our partitioning elements. Oops. Where did we go? Right. And so here, C, our molybdenum here, right, basically doesn't partition, right? Once we're below this temperature, we basically take an infinite amount of time to move our heavy molybdenum elements. Okay, carbide formation, right? So we can arrange these in order of their increasing affinity for carbon, right? Which means their desire to basically suck the carbon out of solution, right? And so we see iron is a fairly weak carbide. Our strong austenite or ferrite stabilizers tend to be strong carbon gatherers. So we can see an example here, right? If we have a chrome molybdenum steel, right, with insufficient carbon, meaning that we haven't, we don't have an excess, we don't have any free, we're not saturated in carbon. If we then add vanadium, right, vanadium will actually steal the carbon from the chromium carbides and then from the molybdenum carbides, right? And then we basically have vanadium carbides in our alloy, and chromium and molybdenum will dissolve back in to form a solid solution in the austenite phase, right? So these carbides, right, basically give us strengthening in the same way that the secondary phases in aluminum have, right? So playing with the alloying elements not only allows us to mess with the austenite ferrite phase fields, but also play with the structure of these carbides to give us additional strengthening, much like we would have in aluminum. Right? We also have, this is some good Indian English here, right? Graphitizes, right? Meaning basically we're going to take our cementite and reduce it to our equilibrium phase graphite. Right, so silicon, nickel, copper, and aluminum, all strong austenite stabilizers, right, will, we won't have cementite in our structure. We'll have graphite. Okay. And so notice these are the ones that, the elements that correspond to our open our closed gamma field is what I wanted to say. Right. So we can get large ferrite grains with, instead of cementite, graphite. So these sort of make the steel behave more like a cast iron, right? That lower concentration cast iron than the steel. Cobalt is neutral in this sense, right? It doesn't cause carbide formation, and it doesn't cause graphitization.
So for the carbide forming elements, for the increasing affinity,
yeah,
that taken into consideration just their stability at the same temperatures, or what is it actually taken into consideration?
I'm not sure I follow the question. What do you mean by stability of what at the same temperature?
I guess a titanium carbide versus a chromium carbide. Because you say you would form titanium carbides before chromium.
Yeah. So this is the affinity here, right, is essentially another measure of stability, right? Not well.
Because we've seen in some occasions where even when you do have titanium, it preferentially forms chromium carbides.
That's interesting. So it could be, so this is basically just energetics of formation, right? This is the enthalpy of formation is how these are ranked. There's no kinetics necessarily taken into account here. Or there's no ranking by dissolution temperature, right? So if you are in the melt and you cool quickly, it could be that, yes, the titanium carbides are more energetically favorable, but they're slower to form, right? So this is ranked basically just by enthalpy of formation, right? Not any other features, right? Again, with steel, everything's complicated, right? So this is sort of like your first guess as to what you're going to see. If you processed it in bulk and had an infinite amount of time, right? As soon as you're in welding conditions, right? I think all bets are off. Okay, so the austenite grain size is a very important structural characteristic of your final steel, right? So austenite, we talked a lot about nucleation of ferrite and pearlite and bainite at the prior austenite grain boundaries, right? So the size of your austenite grain is going to determine a lot. Remember, we said that bainite, if we have big prior austenite grains, we're going to tend to form acicular ferrite rather than bainite, because we don't have enough grain boundary area to nucleate the bainite. Okay. Also, the prior austenite grain size is really the primary factor that's going to determine the toughness of your steel in the hardened and tempered state, right? So the prior austenite grain size is going to have a profound influence on the martensitic structure that forms. Then once you temper your martensite, we'll get to tempering probably tomorrow, right? You're going to end up with very different microstructures depending on the start of your initial austenite grain size, right? And also remember, in alloying, a lot of elements will tend to segregate to the grain boundary, right? And so tin, right, is a big one, right? And so you weaken the grain boundaries, and we have gives us preferential fracture paths through our material. Okay. So, right. This is just sort of a schematic. Here we see our temperature, right, and the evolution of the structure, right. So this is sort of the whole temperature. If we're at lower temperatures, right, we have a nice perlite microstructure with some pro-eutectoid ferrite, right? So this image has to be which side of the eutectoid are we on? Is this hypo or hyper? Right, we've got
Hyper.
It's hyper, right? Yeah, because we've got nice, clean ferrite grains that grew as pro-eutectoid ferrite, right? So basically, we can trace out what our prior austenite grain boundaries were, right? And actually, you know what? This slide's going to take me a little bit to go through all the changes in all these figures. So we'll stop there for today since we're just at time. I don't want